Well, good evening, everyone. Hello, Boston. How are you guys? That's good. Really delighted to see so many of you turn up for the Apache Spark meetup here. My name is Jules Damji. I'm the Community Spark Evangelist at Databricks. I'm not here to pontificate. We've got other pontifications going on, so we're going to be having about three speakers today. We do want to thank Snappy Data. They are our sponsors. All the food you're actually eating, all the drinks you've actually had. Big hand to Snappy Data, guys. Remember, this Thursday, Databricks is hosting a healthcare reception. To those of you who are in Medicare or those of you who are in pharma, this is a good place for you to actually come and meet some of the exciting things actually happening, how Apache Spark is making its way into this particular new vertical. So those of you who are going to be here on Thursday, please do come in. And I want to also introduce Nick, who is the meetup organizer for Boston. I'm really glad that he actually stepped up to the plate and say, Boston meetup should be part of the Apache Spark Summit. So please be welcome, Nick.
Hey everybody, my name is Nick. I'm the organizer of the Boston Spark meetup. I also have some of my co-organizers here. Matt, are you here? Could you raise your hand? We have Matt. Is Yana here as well? I don't know if Yana's here. Okay, yeah. So we're a community organized meetup, and the purpose of the meetup is just to have people from the Boston area kind of come together and share stuff they've learned, use cases they've had for Spark, their war stories, and so on. So if you live in the Boston area or you're visiting, and you want to either speak at our meetup or sponsor an event where you can get your company's name out there or something, definitely reach out to me or to Matt or find us on meetup.com and reach out to us that way. I also want to make a brief shout out to Donna. There's going to be a luncheon tomorrow at the summit for women in big data. And the event is open to everybody, even people who have not registered for the summit. And I believe attendees to the luncheon also do get a free one-day pass to the expo, to the summit itself. So Donna, raise your hand so people can find you. So if you want to learn more about that luncheon, just find Donna. I believe she has flyers to hand out for you about that. Okay, so that's all I have to say for now. I'll check in again later. Back to Jules.
Thank you, Nick. Big hand for Nick for organizing and helping us to put this great meetup together. It's really great to see you guys. How many of you were at the training today? Oh my God, 50% of those. Now, this is really passion for Apache Spark. You guys went through 8 hours of learning Apache Spark. There's going to be another 3 hours of that. And as I said, by the end of the day, you're going to have Apache Spark tattooed under your eyelids before you get out of here. So I'm glad to see such a big turnout. Anyway, our first speaker today is our sponsor speaker from Snappy Data. His name is Jag. He is the CTO at Snappy Data. And if you heard about operational data, which is sort of new thing going on, how do you actually use Apache Spark to do inline memory fast analytics? And he was the chief architect at Pivotal and VMware doing Gemfire, which was the operational database. And today he's going to give us a talk about how Snappy Data actually uses Apache Spark to do inline fast analytics. So please give a big welcome to CTO from Snappy Data, Jags.
Oh, hey, thanks, Jules. Can you guys hear me? Awesome. So should we get started? I mean, still have to, I guess I have the extra 10 minutes. Thank you. Hi, guys. 30 minutes still? All right. Okay, so let me just start by giving a little bit of a context for what we are doing with Snappy Data. It's actually an open source project. And the history is that we built Gemfire, which is now Apache Geode. How many here have heard about Apache Geode or Gemfire? Okay, maybe 10%. So essentially, it's an in-memory data grid. It was all focused on transactional workloads, low latency, high availability workloads, much like Cassandra's, except in-memory was the focus, right? So primarily Wall Street, banks, and then we branched out to everything, right? So today it's being used in Southwest Airlines, runs it, a whole bunch of very high transactional, low latency systems. So as we essentially went to the market, trying to essentially get Gemfire running on top of HDFS, and lo and behold, the market said it's in-memory on top of Hadoop, and immediately people started throwing analytical workloads. So essentially, it's the realization that today we live in a world where increasingly, if you start thinking about streaming applications, the workloads tend to be mixed in nature, right? where you have to deal with the stream, you have to deal with high write rates, you need HA characteristics, you actually need transactional characteristics. I'll explain that. So it's really, essentially Snappy Data. So in some sense, takes Spark to the next level. If you want one way to think about Spark, obviously it's a confluence of interactive streaming and batch processing, right? That's how Databricks defines it. But still the batch design center, right? So what we're trying to do is to say, can we in a way take what we built with Gemfire and sort of push it into the executor itself in Spark, right? Sort of essentially coming up with the next generation, if you may, operational database that primarily operates in main memory that also offers OLTP semantics, essentially streaming OLTP and OLAP in one, and we have a bit of innovation around probabilistic data stores. So that is what it is. So again, it was founded, it's a spin out of Pivotal. We were initially in VMware, and then Pivotal drove essentially Gemfire, and then started to think about how we build this out. We were spun out in 1/1 of last year. It's about 25 engineers, and we are essentially the investors are Pivotal, GE, and GTD Ventures. So this is the key. Mixed workloads are everywhere today, right? And what you see actually is a virtuous cycle between what happens in the stream processing layer, followed by the fact that streams are continuously emitting data that I have to write and save it into a store. So I really need high write rates into the store. And then off you go into the store, and then you essentially land up saying, I need to analyze the store, so I'm running interactive queries in the store. And then quite often what you'll end up seeing is today, right, where you might be exploring data sets and you might be creating a model and you want to inject that model back into the streaming pipeline, essentially a virtuous cycle, right? So here's a simple use case in the telco domain. So telco, if you guys have been following the telco space, given that the margins are shrinking, there is an increasing demand for use cases like location-based services, another use cases in the network optimization space. And the location-based services, which is kind of perhaps illegal here, but if you look at out in Europe and stuff like that, a subscriber can opt in for advertisement. So based on where you are, an ad could be placed, right? So there, you'd see that there are typically stream processing has been more about apply a rule on a small window of data and maybe I raise an alert, right? And what is increasingly happening is that can we go from stream processing to stream analytics, right? Where I'm not only just looking at a small window, but I need to really correlate. I may need to do a join. I may need to do top K analytics. And all of a sudden, essentially, you're looking at the same kinds of optimizations that you're used to in an OLAP engine, a columnar database engine that now needs to be applied in the stream processing layer itself, right? And that's kind of one of those interesting sort of confluences, right? Saying, hey, the stream processor design center was one. You have the columnar database that's a different design center, but they in some sense need to come together so that you can realize a richer set of analytical applications, right? So let's just go a little bit deeper. So here is what I'm showing is, stream represented as a time window, and you are essentially taking a high velocity stream and writing essentially potentially to a table that is in some sense ever growing, right? And then you may have one or more reference data tables. So for instance, in this sort of telco example, you have call data records coming in at a high rate. You might be processing it essentially by doing and sort of massaging the data, writing into this table that is essentially time series data that's perpetually growing. But you also need CRM data potentially to look at saying, okay, can I essentially look at the profile of the subscriber so that I can do efficient joins and things like that. So one of the immediate challenges there is how do I now do a join between what's happening in the stream. Now the interesting thing is that even in this domain, it's going from saying, oh, I just need typically look at the window of a few seconds to increasingly going and saying, I need to actually process the stream windows that could be an hour, even in fact for a day. And I'm essentially sliding that window every few seconds. In other words, I'm looking at data. So for instance, do I see the call drop rate, go up or down a trend for the last hour that I'm essentially processing every 2 seconds. But to do that, to make effective decisions, I need to now join the data with other reference data, right? So you're essentially joining the stream with the historical data and potentially joining to reference data. Now the key thing is that the reference data itself could be in real time, is also getting updated through external other systems, right? So what you really need is not only do I need joins and that kind of capability along with the streams, but I also need support for fast writes, updates, exactly one semantics, and in fact HA. And if you think about it, I mean, if you have a situation where a single stream that was coming in, inside Spark landed up being distributed, essentially, or either I forked the stream into multiple streams, or I just landed up doing distributed processing, you ultimately realize that to write into the store, if let's say I'm doing aggregations, right? Essentially doing counters out and writing it into the store, I actually need, in fact, I do need transaction semantics. So that becomes a very important consideration. On top of that, once I have all this data emerging, I want to turn around and have a BI tool essentially run interactive queries on this data, right? And all of a sudden, if the interactive queries are really scan-oriented, let's say I'm doing an aggregation of some sort, how do I do it at high speeds, especially when the data is coming in and I'm constantly doing high writes into these tables, right? So you not only do we need the ability to support high-speed scans and aggregations, you also need high concurrency support. In other words, can I get a whole bunch of users that could either be exploring data, but more importantly, applications, online applications that are also can run queries on this EFMA real-time store. And on top of that, you also may need point lookups. So what you really see is that you need all the characteristics that you'd see in a high-scale, OLTP-like store like a Cassandra or a Gemfire. You also need the capabilities that you'd see in a very modern column-oriented MPP database. And of course, you need optimizations in streaming solutions, right? Because one of the interesting things is that if I'm essentially joining a window, let's say, which is an hour long, and I'm incrementally sort of sliding that window every 2 seconds, can I do incremental processing? Incremental processing becomes, rather simple. Incremental processing becomes rather simple if I'm doing a sum, right? Hopefully this shows up. All right. But incremental processing becomes rather difficult if I'm doing, let's say, a median or some operation that requires me to essentially operate on that whole window, right? So those are interesting challenges. So essentially, when it comes to mixed workloads, the point is that the design center is really also a confluence of what happens in a columnar database, what happens in a row store, and if I'm running interactive aggregation kind of queries, you might have to think about, hey, how do I schedule, essentially something that's going to suck up all my CPU when low latency operations are going on concurrently, right? On top of that, if I'm dealing with a stream that is sort of infinitely giving me more data if it's time series, so your data volumes are very, very high, right? In a whole bunch of domains. If, let's say, if you're dealing with IoT or industrial IoT, you're accumulating terabytes and terabytes of data on a single day. So how do I essentially do interactive querying on such a large volume? So increasingly, you would see that there is a momentum towards saying, can I have probabilistic data structures, essentially data structures that can synthesize something very, very small, keep it in main memory, on which I can interactively ask interesting questions. So today, if you look at, I don't know why it's not. All right, I just have to do this, I guess. So today, most of, if you look at the standard answer, it's all about Lambda, right? And I'm not going to go into Lambda, but it's about taking, new data as it's emerging, writing it to a speed layer, which is, some sort of Storm, Spark streaming, combined with a store that operates and offers you linear scalability like Cassandra. And then you also write it to a batch layer. And then it's up to the application to, in some sense, do the stitching between all these systems. So our take is that Lambda, our focus is in the streaming and the interactive layer. But Lambda to us is rather very complex, right? It's complex because in some sense you have to learn and master multiple products, different data models. You have to tune these different products. And the challenge actually lies, when you actually go into production, right? And all of a sudden, if I have new requirements coming in that causes my schema or my data properties to change, and all of a sudden I have to now touch the streaming layer, the streaming app. I have to touch maybe my Cassandra store because my structure has changed. And of course, then if I'm running SQL on Hadoop, again, that application also has to change. So it's just a series of changes requiring, in some sense, an army of developers to always be on it. And then it's wasted resources. In fact, it's much slower. One of the things that is not really talked about much is the amount of copying that happens in these modern day clustered systems, especially the ones based on Java, right? And in big data analytics, I mean, the single biggest cost, if you actually analyze, you're paying is the amount of copying that's going on. And if you look at the sort of the graphic on the right, it's simply depicting a simple clustered store that is taking a piece of data that's coming in on the network and replicating it synchronously on another node and acknowledging it back. And you're talking about 7 or 8 copies going on, let alone potentially inside the JVM, the from and the to spaces. The guys who looked at JVMs closely, you know that there's a lot more copying going on, right? So now, similarly, if you now look at the common architecture with, let's say, Spark streaming, and I'm essentially using a NoSQL store on the back end, that also is pretty inefficient. Now, it's fairly efficient today if my streaming application is rather very straightforward. In other words, I'm just taking my stream, doing some basic processing just on the window, and I'm continuously writing, let's say, into Cassandra. But then if I want to turn around and say, can I ask an analytical question? Can I ask an insightful question on the data? You have no choice, but you're left to saying, hey, let me run that query on Spark. And all of a sudden, I mean, those of you who paid close attention to these connectors, you can only sort of push down predicates, you push down projections. But then, if I'm running an aggregation query, all of a sudden, I'm having millions of data points that are essentially coming out of this NoSQL store into Spark, lots of copying, serialization, deserialization going on. And also Spark, I mean, those of you who followed sort of Spark's tungsten optimizations and the vectorization optimizations, you lose a lot of those nice, good richness because of the data format changes that are going on. So the question really is, can we simplify and optimize? So that's really our proposition with Snappy Data. So in a nutshell, again, Snappy Data is a single cluster. Rather than sort of saying, here is a Spark cluster and here is a data store cluster, we're taking the data store and fusing it in Spark. So one way to think about it is that we're taking Spark from being a pure computational engine and in some sense turning it also into an operational database, right? Sort of making Spark much more applicable to a lot of these real-time mixed workload scenarios, right? So Gemfire, which has a real-time, low latency, high availability design center fused with Spark, to us, which is fundamentally a very high throughput batch-oriented design center, right? So Spark, I mean, a lot of folks, HA is not to be confused with Spark's failure detection and failure recovery models, right? HA is all about saying if there is a failure, the system and the cluster is able to detect failures in milliseconds, and it's able to sort of fail over client connections within that small period of time. Imagine you have a real-time application that's connected and end users are connected to the system. How can I essentially detect and switch over very, very quickly? So the HA semantics truly requires you to have a true distributed system underneath the covers, right? So in a way, what we're saying is that we're turning Spark from a computational engine to what it looks like here, which is we have embedded essentially an in-memory store. It's a hybrid in-memory store, so it has row-oriented storage, much like what you would expect in an OLTP engine. It has column-oriented storage, very similar to how exactly Spark essentially manages column-oriented data. If you take a data frame and you do a cache operation in Spark, it essentially creates column-oriented structures, right? I mean, it essentially creates batches of columns, and it does compression. So we do the exact same thing, right? So when it comes to column-oriented data, we manage it the way Spark manages it. The data is in fact mutable, so you can essentially index on these data structures, mutate it, run transactions on it. I mean, the architecture fundamentally is a bit different than Spark in the sense that these executors now are actually coupled to one another more closely than it is in Spark. Spark essentially has a master and a whole bunch of worker strategy. In our world, given our high availability semantics, we make sure that the executors can in fact talk to one another so that we can detect failures very, very quickly. So it's like saying that here is a cluster, it's a database cluster that's up and running, and Spark executors are running in the same process space where we manage our data sets. But we also allow Spark clusters to talk to this database, right? So you can have an external Spark cluster that's running in Yarn, Mesos, what have you, which is purely a computational grid. And you can still work with sort of Snappy Data, much like using connectors. And even these connectors really fast because of how we parallelly process data, given that the data structures are very similar underneath the covers. All right, so yeah, so at a high level, again, it looks like this. I mean, things in blue is Spark, things in sort of the boxes in kind of light green is what we added to Spark, right? So you can, so the nice, beautiful thing here is that the Spark ecosystem is so rich, right? Which is something we didn't want to work on, right? The ability to say, hey, can I essentially work with HDFS cleanly, S3, I can work with Cassandra. I mean, all sorts of data sources. In a way, I can sort of federate data from any of these data sources relatively very, in a simple way. The transformation APIs, just really amazing, really awesome amount of richness there, right? And sort of the SQL thing, in Spark SQL, it's all about selects. So we essentially give, obviously, given that we do mutations, we had to make sure that you can do inserts, updates, we support keys, you support constraints, all the stuff that you'd expect from an SQL engine. The catalog itself is also fused together, right? All right, so let me just go a bit into the architecture of the store. I have no idea how much time I have. Did I elapse already 30 minutes? 10? Oh boy. All right, I'm going to skip quite a bit here. All right, so essentially what you'd expect from a store, right, which is in Spark land, which is any of the tables that you have. Obviously, you can come in through SQL and access it, or the tables can actually be visible as simply as data frames also. All right. So row tables allows you to do random writes. You can have key-based lookups very fast if I want to do very low latency selective operations, right? What you would expect from a NoSQL-like store. So you can essentially have an inbound ingestion stream being processed where I'm writing something to row tables. Some stuff goes into essentially if the data is ever increasing, you can write into column tables. And the way we support mutability in column tables is that we have a row buffer, what you would expect in, for those of you know MPP databases. You have a row delta buffer that essentially is where we initially do the writes, and periodically the writes are transferred into the column table. I'll touch on this technology called, we call it the synopsis data engine. We've embedded probabilistic data structures into the SQL engine, into our engine itself, such that it's visible to general purpose SQL applications. API is pretty much Spark compatible. If you're familiar with the Spark data source API, it's pretty much acts as another data source. And we have extensions on the Spark session API so that you can do updates and deletes and those kinds of operations. All right. If you're doing SQL, when it comes to selects, our syntax is mostly what Spark SQL is with a few extensions, so that we support cursors and things like that. And of course, when it comes to SQL, you can obviously come through JDBC, and we support all the SQL syntax of updates, deletes, and all what have you. The extensions on the SQL side are also offered through Spark options, right? So if you look at the DDL, we can do things like, hey, can I co-locate multiple tables together? Can I partition it on a custom way? Can I partition by primary key basis? Redundancy essentially allows us to say that, hey, if I create a piece of data, I can have one or more synchronous copies inside a cluster, and I can have asynchronous copies across, let's say, WAN boundaries, right? So things like that, right? Pretty straightforward. We also added a few extensions to Spark streaming to make stream processing more appealing to SQL developers, right? So that, for instance, one of the things we offer is, so you can do essentially declaratively, you can define streams using SQL, using create stream table. This is based on a project that Intel did. As structured streaming emerges and becomes more like 1.0, we essentially plan to integrate with that. I'll just skip this. Essentially allow you to register what's called as continuous queries, and the continuous queries will essentially run as my stream is emitting data, right? And then you can easily take the results of a continuous query and essentially write it into our column or row store very, very easily. So this is what I touched on, how we, this is going into details for how we support updates and deletes. So I'll touch a little bit on sort of the statistical data structures, right? So like I said, one of the challenges we have with this high velocity streams is that, hey, my data is continuously growing. How am I going to run a query if my data is going to be 10 or 20 terabytes and I'm claiming that I can give you interactive speeds? It's simply not possible, right? Unless until I have tens of thousands of cores available. So the idea here is to really take, understand data, characteristics of distribution patterns, for instance, characteristics of data, and create essentially these data structures, right? Like sketches and samples. I mean, sampling is the simplest way to think about it. But if I create these data structures, can I essentially run a SQL query? And obviously, the trade-off here is accuracy, right? In other words, I can give you a 100% correct answer. I'll give you an answer. It's, the question is, can I use algorithms to tell you how good my answer is, right? That's the key thing here. And the nice thing is that, if you look at the graphic on the right, it gives you this thing saying if I'm visualizing big data sets, how can you tell a difference between a 100% correct answer and a 90% correct answer? You can't really tell it. And I'm going to skip all this, right? The probabilistic details. I mean, we use things like count-min sketches. We support count-min sketches to work on time series data. We do stratified sampling, but we also support not just static samples, we support dynamic. In other words, if I have a stream coming in, can I essentially build a stratified sample over time also? Okay? I mean, there are a bunch of other optimizations. So let me just see if I can show you guys a quick demo, assuming it's still, how many, do I have like a few minutes? 5 minutes, okay, excellent. All right. Maybe I'll just stop in a minute or two and then take some questions. I mean, essentially what this is showing is a simple Zeppelin-based notebook where we're comparing essentially Snappy Data's in-memory performance to Spark caching and also to Cassandra. I was going to actually run it. I don't have the time. This is actually going to be visible through our blogs on our site. The project is open source, so anybody can download it, try it out. It's pretty simple, right? So what I'm doing is I'm taking 100 million records in a 2-column table. It's running on AWS on a compute instance with 4 cores. And we're simply running an aggregation query that says, hey, give me the geo and an average bid. And I'm grouping. And we're saying, hey, how fast does it run, right, based using. So I'm not going to run on the Spark side, but if you look at on the Snappy side, if I run this thing, oh, sorry, not this one, not the right one. So, I mean, what happens is, I ran it and, I averaged the query time scanning 100 million records and doing a group by took about 190 milliseconds. The same thing on Spark Cache would take about 2.7, 2.8 seconds. And the reason why we see that optimization is some of those vectorization changes that have gone to support Parquet and Spark, not yet there for Spark caching and things like that. So there are a number of optimizations because the store is so embedded, we could capitalize on, right, in Spark. And what this is showing now is that, hey, I'm creating a sample table on that same table, that's 100 million. And if you see this, even though the count is 100 million estimated, the real count is only about 1 million. It's a 1% sample, and I can simply run the same query on the sample, and it literally took only 40 milliseconds. In fact, a lot of this time is because of Zeppelin and other things going on. Anyway, so hopefully that gives you guys a sense for what we are up to. Are there any questions?
Yeah, in terms of your query optimizer and SQL parser, what have you done? Invented your own or borrowed?
We had our own parser in the Gemfire world, right? So we actually blend what we have done with the Catalyst engine. I mean, essentially, Catalyst is pretty extensible. That's a great part about Catalyst. So we essentially extended and used those extensions to do what we needed to do.
I see.
Any other question? Right here.
One of the biggest challenges I'd faced with a streaming solution was, accessing global state in your stream, just like you were talking about earlier. And a lot of approaches that solve that will partition your stream, and then you have some local in-memory store on every partition, and that's how you handle that. Is there any sort of optimization going on underneath the covers to delineate between kind of stream partition level optimizations versus needing to access the global state?
That's a great question. Yes, so what we do is our design is very driven by saying do the least amount of shuffling in such systems as possible. So one of the things we do is, let's say you have a Kafka engine that is actually pumping into Spark, which is pumping into our store. We pay attention to how Kafka is partitioned. And to greatest extent possible, we would say that, hey, my partitioning is going to rely on my parent's partitioning. And if you can detect that it is a Kafka partition, then we would just retain that partitioning, unless until the user said, no, 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 I do want to partition it this way. So we essentially save on any of that shuffling cost. Gives us huge improvements. Yeah. One other?
I was wondering if there is any user access control here, or maybe if you have more than a few people in the team, perhaps you want to have some kind of just read-only access for certain tables and then have some user space.
That's
where they
correct.
Can play around.
Right. It's also, even though it is based on Spark, it's also a SQL database, right? I mean, it's like Spark SQL. So when you come in through SQL, there's absolute access control, much like what you would expect from a SQL database. One last, maybe? Okay.
Going once, going twice. Anybody from here? This file's neglected. You had a question? Okay, I'll just run down.
Are you able to keep up with the updates in Spark versions? Is there any time lag there?
So the question is, are we able to keep up with the update rates in Spark?
Versions, yeah. Are you on 2.1?
Oh, yeah. Okay, thank you. Yes. So we have a lag right now of about a few months. Hopefully, we will retain that. So right now, we are working on releasing a product with Spark 2.1, which should get released in about a couple of months, a month or so. Yeah. So we don't know how that's going to pan out in the future, because there are a number of things where we're extending some of the internal stuff to do what we need to do, right? So we're trying to figure out, saying, hey, is there a way we can contribute it back? I mean, a lot of the changes we've done are sort of kind of tied to how Gemfire works. So it's a bit difficult to say, hey, can we contribute? But we are attempting to do that. So hopefully that works out. It is an open source Apache V2 license project, though. So okay, thank you.
Okay, give a big hand to Snappy Data. Over to you, Nick.
All right, it's Nick again. So our next speaker is going to be Ted Malaska of Blizzard Entertainment, or is it just Blizzard? Makers of very many well-known video games like StarCraft and World of Warcraft and Overwatch, and I'm sure you've all heard of at least some of those games. And Ted is going to be talking about hacky tricks that can make you a Spark rock star, because writing your typical Spark program, or maybe a very big Spark program, is generally not the smooth sailing all the way. At some point, you're going to have to pull out some dirtiness to get through to the end. And I know I've had to do the same myself on several projects that I've worked on. Some really nasty and depressing stuff at times, although not as depressing as what happened to Atlanta last night. So without further ado, Ted Malaska and how to become a Spark rock star by playing dirty.
Let's see. All right, it's on. Can everybody hear? All right, cool. Okay, so a little background. This page is essentially to say, oop, did I leave my phone down there? Let me just grab my phone real quick. Yeah, it is. All right, sorry about that. Oh, all right. So this page essentially says that I know what I'm talking about, so I won't spend too much time on it. I wrote a book. I used to work for this company called FINRA. They recently published a blog about a system that I help architect. I think they're bringing in 72 billion records a day into a real-time graph database that real-time connects points on all the stock trades that happen in the US. Then I used to work for Cloudera for about 4 years, and I interacted with about 100 different companies. And after I was fully vested, I'm now retiring at Blizzard, being the group technical architect for data, cloud, and test. And I've contributed to HDFS, HBase, Flume, Spark, Avro, Kairos, Kafka, Scoop, Pig, Kudu, Yarn, MapReduce, and I'm sure there's some other ones I forgot. And if you don't know about Blizzard, like he said, Blizzard and Activision are the largest American game company that exists. These are the Blizzard games, but if you don't know Blizzard games, you know Activision games, just like Call of Duty. And if you don't know Call of Duty, We also have King games, so if you've ever heard of Candy Crush, we have that also. So any genre, good part of you, if you play video games, you've heard of some of these. I wrote this like 100 billion thing when I was like in the first couple weeks. There's a very good chance we're going to pass 1 trillion messages a day in terms of our pipeline. So we got data. All right. So before I get started, I just want to take one quick picture just to show my wife that people actually showed up and listened. She's like, you're going all the way to Boston. There's no one who wants to hear you in Boston. So thank you for that. Yeah, because I'm in Southern California, and I just flew out this morning, and the temperature dropped 50 degrees at least. Okay, so the first one is debugging and unit testing, right? So how many people debugged their Spark on their local console? How many didn't even know you could do that? All right, a couple didn't know you could do that. Okay, so I never run something on the cluster until I already know it works. How many people run things on the cluster and then you have an exception and then everyone on the cluster has seen your exception and they're like, hey, Bob, why are you having so much trouble? And you're like, oh, I'm debugging my stuff, right? Well, everyone knows that you're debugging your stuff. And if you're in the cloud, how many people are in the cloud? All right, if you're debugging your stuff in the cloud, what does that mean? That means money, right? Unless you have deep pockets and you have no problem paying AWS for storage, for execution. So running things locally is really important, and if we have time today, I'll actually do it up on here. We'll actually do in debug mode. Just the ability to harden, to unit test, and to, unit test. Who unit tests their Spark code? All right. Because if you don't unit test, you really can't pass on your stuff. So trick number one is kind of boring, right? Debug and unit test. This is a little piece of code that I put into every single one of my applications. All this is essentially saying is when I send in a parameter, my first parameter is always is local. If I am local, I'm using the local JVM. If I'm not local, I'm spinning up in Yarn or whatnot. And this works pretty well. All right, I don't have a unit test example. I was supposed to get it, but I wrote this on the plane. And the next one we're going to talk about as we go into the next one is parallelizing objects. And this becomes really important when you're doing unit testing. But I want to save some time, and I want to do some parallelizing objects that are nested. How many people do nested structures? How many people didn't know what nested structures were until they came here today? Okay, one person. 2 people. Thank you for being brave enough. So tomorrow I have a whole talk on this, so if you come to that, you're going to get like 25% of that right now. So nested structures, we'll see in a minute, are things like JSON. You can have tables. Protobufs are nested. What are nested structures really good for? First is parent-child relationships. Does anybody have parent-child relationships in their data? All right. If the parent-child relationship is less than 1 to, I want to say a couple million, then this is going to be very attractive to you, right? The other thing it's really good for is if you're doing things like Cartesian joins, where you can decrease the expense and cost of a Cartesian join dramatically. We're not going to go into that today. We're going to go into that tomorrow. All right, so what is a nested structure, right? So this is a JSON, right? So our JSON right here has group, time, value, and nested. And nested has 2 columns. So this is pretty common, right? Nothing big here. So if we wanted to read in JSON, we read in that path, and we write it out. And what we'll see is it's a row of rows, but the way Spark does it is when you read it out, it's wrapped arrays. But I know they confuse the heck out of us. When you put it back in, it's row of rows. Now you can also take these nested structures and you can make them tables because they're data frames, and you can run SQL on them. If I run the given SQL here and I say group and nested column, what you're going to get is you're going to get that data, which is still nested, right? So that might not be useful to you. But you can also do things like lateral views on the data, which will pump it out and let's see if it has a good example. Yeah, so if I pumped out the schema of this, you'll see that the table is now flattened. So what is that actually doing? That's actually doing the join between the parent table and the upper table, right? And so that's essentially giving you a denormalized view. So the big difference between a denormalized view and a nested table is in a denormalized view, every time you have a child, you have to replicate the parent, right? And if you're multiple levels deep, you have lots of parents to replicate. So you can see right off the bat, in terms of memory, nested tables are going to save you on memory. On disk, they're going to save you space on disk. And I don't go too much into it, but if you do save your file formats as Parquet, you only actually read the columns you ask for. So if you're only asking for the subtable, you only read the subtable. If you're only asking for the parent table, you're only reading the parent table. So again, if you have nested structures, very, very good. The other thing is joins between parent and children are free because they're merge joins, right? Imagine like a zipper. They just zip together. You don't have to do a shuffle. All right, so if you've never done nested tables in Hive, this is what it looks like. You'll notice that there's a little funky thing. There's a colon next to title and maker and size, but there is not a colon next to person and cars. This is the number one thing that people mess up. Why is that colon there? I have no clue. I guess Hive likes inconsistencies. But this is how you would structure it, right? And this is the Spark representation of how you would put this data in, right? So again, it's a row of rows, and you can have sequence of rows, right? And I'll walk through, if we want, this was what we'll use for our debug example. Now, we can make this into a data frame in a couple different ways. One is we could create the table and then make the rows. And then what we can do is steal the schema, right? And in the old days, when struct type was a little bit more cumbersome to build schemas, this is the trick I would use. I would query the table. I would ask for no records. And that would execute extremely fast because I'm not asking for anything. But it would give me the schema. And then I could use that schema with the RDD to make a data frame. Make sense? But nowadays, it's so easy with struct type just to make a struct type because there's this nice little add function. But notice that whenever you're doing nested types, you have to have two struct types. And the second struct type takes in the first struct type. Does that make sense, everybody? And then the same thing. Then you just make the schema there. All right? Now, in the new world of data sets, you could go all out and make case classes, right? And it works out the same way. You have child case classes to other case classes. And when you read in that JSON, you can just say as that case class, and now it automatically goes to that object. So you don't have to use that clunky row object where you have to say get as, and then put the type in, and then the field name. This can actually compile at runtime, right? I mean, this will validate the code at compile time, as opposed to blowing up at runtime. Any questions on nested structures? So yeah, if you have parent-child relationship, if you have Cartesian joins, you really, really, really need to think about using them. They're less memory, they're less serialization over the wire, they're better for joins, and so on. The only trick to them is if your table is highly mutable, you'll have to rewrite the table if you want to add additional children, right? Because they are always written together. And there's tricks to doing that. We'll talk about it later. But essentially, you want to use bucketing and sorting. The next one is the idea of big and small. Okay? So big and small, I have a story about this. I was working at one bank once, and I went to one group, and they told me, they say, Spark sucks. And I was like, okay. It says, this job takes 2 hours to run with Spark. And I was like, okay, well, can you show me the code? So they showed me the code, and it was, I want to say it was somewhere around 1,000 lines. And I was like, okay, first of all, if I'm not going to read this, you're going to tell me what it's doing. He says, okay, so we have mortgage statements, and everyone has paid their mortgage at certain intervals, and we're just looking at how frequently they pay on time, and do they ever miss dates, and we want to do causation analysis on their mortgages. And I looked at all this stuff, and because they were doing causation analysis, they're doing a lot of sorting, right? You want to know what came before what and what came after what, right? So that was the 1,000 lines of code. And I was like, well, how many mortgage statements does a single person have for a single house? You know, they did the math, and it's a couple hundred, right? Somebody in the audience can tell me the exact number. But it's a couple hundred depending upon the length of your mortgage. And I was just, why don't you just do a group by and then do everything in local memory, right? Do you guys know you could think like that, right? And when we did that, the job went from multiple hours down to 2 minutes. And what the thing is some people have forgot with Spark is if you can do divide and conquer with your job and get back to a single JVM with a single thread by separating and partitioning your data, the moment you do that, you should get out of Spark. Spark is for the big problem. But Spark can help you execute the small problem in parallel without using Spark. Does that make sense? Is that a new thing to people or no? So the idea of that is use Spark less, right? Use Spark, but use it less. So if we have time, if I finish early, I'll show you some examples of small grouping. If you're doing small grouping, you can do a group by or reduce by key based on, in this case, would be the house and the person, right? That would be your key, and you would get all the records. Then you would have the collection in memory, and you can do all the sorting you want locally on your 400 or so mortgage statements, and it's going to go really fast. The other one is big groups. So if you ever go to the New York Stock Exchange, right, if you want to do causation analysis on price, you have a lot of transactions. So if you did Apple for a month, how many transactions does Apple have a month? I think it's got to be close to the billions or hundreds of millions. And you can't fit that into a single JVM. So the group by feature is not going to work for you. But what you can do is you can do essentially grouping by time periods, grouping by windows. And what you essentially do is, let's say you want to do a week at a time because you can fit a week into memory. What you can do is you can send the entire week, and you send a little bit of overlap for this is one partition, this is another partition. And you can do all the windowing operation for that week, and you just have to redo a little bit of the buffer. But it's the idea of separating and doing divide and conquer. And we'll go into the code if I get time. The next one is driver threads. How many people have multiple threads in their drivers? 1, 2, 3. How many people knew that they could have multiple threads in their drivers? All right. How many people scared of multiple threads in their driver? All right, good. All right. So this happened all over the place, and this happened at Blizzard a couple times. So I went to Blizzard again, and the very first time I got in there, they're like, Spark sucks. I'm like, okay. I have a general trend. If somebody says Spark sucks, at this point, I'm convinced that the developer probably doesn't know what they're doing. But so there was this job that they were running. It was running on like 2,000 cores. And it was converting a couple megabytes a minute of data. And I was like, what's going on? And so they were converting a partition at a time. And a partition certain partitions were big, certain partitions were small. So if there was a small partition, it would do that job, and it would only fire like 5 cores. And it would finish in like a minute. And then it would go to the next partition. Let's say they had 7 cores, and it would finish in like a minute. But it couldn't go faster than that. And it's this idea, have you guys ever heard the buying egg metaphor? So if you want to buy a dozen eggs from the grocery store, you have to get in your car, you have to go to the grocery store, you have to buy an egg, you have to put it in your car, you have to go back home, you got to put it in the refrigerator, and then go get another egg, right? And it takes a long time to buy a dozen eggs, unless you just buy a dozen eggs. So the idea here is if you don't know the quantity of your jobs, but you have a lot of horsepower, you can either bundle your stuff together by doing something crazy by saying, I'm going to put all the partitions together, and then I'm going to remember the partitions at the end, and then I'm going to separate out the files because I remembered which files came from which partitions. Or you can just start a whole bunch of DAGs simultaneously to do all the work in parallel. So we did this on that job I told you about, and it went from 6 hours to 6 minutes, right? And the whole idea is we're just better using the cores we have. And as you use the threads, the multiple DAGs will share the shared resources of the Spark application, and you'll be able to see all of the separate DAGs in parallel on the Spark UI, right? So something to try out. All right. Yeah, and I've done up to about 100 threads in parallel on the driver, and I haven't ran into a problem yet. I guarantee there's some kind of maximum there. I haven't hit it yet. Any questions on driver threads? All right. And how to do it is pretty straightforward. You just use a regular Java thread pool executor, some runnables, and you use atomics to make sure you know what's going on. One trick that we ran out of memory on, and be careful of this, is we had thousands and thousands and thousands of partitions, and we fired all the runnables at the same time, even though the thread executor was only going to do 100 at a time. But the sheer mass of all the runnable objects ran us out of memory. So the idea is just to stagger your runnables with your thread pool. Okay, know your shuffles. All right, so if you're writing SQL, this is more impactful for you. If you're not writing SQL, you're probably aware of this. But there are several different types of shuffles in the Spark world, and they all hurt differently, or shuffles or joins. So broadcast joins are great, but they can only be used on a small amount of data, right? And I've seen people broadcast tens of gigabytes. Not a good idea. Probably you want to stay underneath 1 million or so records. Once you start getting over 1 million or so records with your broadcast, you got to start asking the question, am I doing the right thing? Coalesce is not really a shuffle. It's just reducing your partitions, which is helpful. Partitioning and ordering, like sorting within your partition, this is where things start to get a little shaky because back in the old world of MapReduce, how many people did MapReduce? Okay, a couple. You didn't have to worry about partition size. How many people have ran into exceptions with large partitions in Spark? Yeah, that sucks. So just be mindful of that. You need to make sure that you have your partitions small enough. Normally partitions want to be somewhere less than ½ a gig worth of data. This is obviously one of these like shady areas that you can add more JVM to solve the problem, but you got to be careful. Bucketed and order joins. How many people do bucketed and order joins? How many people know what bucketed and order joins are? So bucketed and order joins are very similar to the nested structure, but they're also different. And what you essentially do is, bucketing is just another word for partitioning. And you can do it in Hive. And then if you sort within those buckets, and you sort 2 data sets and partition 2 data sets of the same structure, that you can read in those partitions in parallel and join them on the read. If you do this, the read is very inexpensive. I did this once at a company that does medical records, and I want to say they had 18 billion medical records. And what they did is they got data every week, but they wanted to do causation analysis across all the weeks together. So instead of taking 3 years of data and reshuffling it every time they had a new week, they just made sure every week was bucketed and sorted in the same way so the readers could read in the data together and it would always be ordered, right? So there's 0 shuffles. And in that, I think we took a 3-day job down to 10 minutes, something like that. So shuffling is bad, and if you can avoid it, do it. And then there's the shuffle, right? And the shuffle with sort. Shuffling is probably the worst thing you can do because there's tons of network, which isn't too bad, but it's the serialization and the deserialization, right? So if you can avoid shuffles, avoid shuffles. If you can move them to a reduce by key or something like that, go that route. And that's the 5 tricks. And then I'm just going to go into some code until they kick me off. Does anybody have any questions about those tricks?
For For the use cases of the multiple threads on the driver,
Yes.
I'm thinking that maybe one of them is when you have less partitions on HDFS than the overall number of cores and executors that you have, and you want to take advantage of the other cores. But if it's the opposite, which you have many more, 1,000 more partitions than the cores that you have, is there also applicable, or in that case, the potential of a Spark with one thread is going to be enough?
I mean, so the main thing you have to consider when you're deciding if you're going to do it, this is a class I do for O'Reilly. I just have it up because I did the class this week, but there's an image in here. The main thing is, when you think about your executors, they have tasks, right? They have n number of tasks, which is equal to the cores or whatever. And if you think about those as pay tolls on a highway, right? If you're not using all of the tolls, something's wrong. If you're using all the tolls, then good for you. Now, if your partitions are really small, that's another problem. It's not as painful as it was in MapReduce. MapReduce, you could get death by partitions, but you can still suffer from that here. If your partitions are too small, a coalesce shouldn't hurt you too much. But does that make sense? So if you're not saturating your cluster, so the big tell is when somebody says, well, I'm using Spark as hard as I can, and then when you look at the cluster and only 2% of the CPU is being used, obviously something's not right. The main thing in cloud and not cloud is you should have your boxes up past 90% utilization. If not, you're just wasting money and time. Does that answer your question? Especially in the cloud. If your nodes aren't at 90%, you're just throwing money away.
All right, so I have a question. So which Blizzard game is the biggest data hog? I mean, is it WoW, or is it Battle.net, or is it the forum trolls, or what is it?
That's a hard question to answer because there's different systems that they funnel to. And we're still working on centralizing everything. Yeah, I don't know the exact answer to that, but it really depends on we're pulling in their metrics, we're pulling in message data, and we're pulling in logs. So it really depends upon how how they do their stuff. Obviously, the systems that are sending more logs are sending more data, right? Just because of sure bulkness, but yeah. But sometimes it's not necessarily the game; it's just all the clients. Think about how many concurrent people are playing all the time.
Yeah,
it's a lot.
I'm one of them, so
yeah.
I'm contributing.
So yeah, the nice thing is the planet rotates, so we get a nice spread of users all day long instead of everybody hitting it all at once. Anything else? Okay, so let's go to some code, and then tell me when I'm supposed to get off. So here's just a quick example of how we can debug. This is the code I talked about earlier. We're going to be reading in the JSON. The JSON for here is nested JSON, so it's just this file right here. Oh, yes, there you go. Whoa. All right, and then I'm just going to go here, and I'm just going to say debug. I know this is rocket science, but some of you might not have seen this. Now, what actually happens is when things are executed on the executor, they're in different threads, and there's different accessibility things. So when I'm inside executor code, I can't necessarily access the driver code and vice versa and stuff like that. But you can see here, I'm in a for each on a data frame, so I'm actually inside executor code. And I can go to this row now, and I can actually say, oh, there's the schema. There's the values, right? Oh, those are small. I can't make those bigger. But trust me, those are right. But the other thing is, what I've done at some places is we'll agree upon a data structure, like a table, and then I'll either take a sample set of data from the cluster and use that as test data, Or if I'm working with a business user that has like use cases, they want to make sure, like if you're doing ETL or something like that, you can actually make it so in your Git project that they submit the data set. So the non-technical people submit the data set to test out different scenarios of the outcome, right? And since, and when you write, like if you said save to table, I don't think I'd do that here. But if you write, it just writes right out to your local system, like that's your distributed storage system. So it reads and writes from that. If you're using HDFS, it should be transparent. If you're using S3, it should mostly be transparent. Yeah, and then I can debug in the driver as well. And I just continue. And oops, I got to get out of the executor. And now I'm in the driver. And obviously when you're in the driver, when you look at a data frame, it's not pleasant, right? But if you wanted to look at a data frame and make it pleasant, what you would do is you just go like this. Add watch. And where to go. And then edit the watch. Where's my edit? I'm going to say new watch. JSON, data frame, collect. Right? And then there's my collection of the actual things, right? Now, everybody knows the difference. Now, everybody knows you shouldn't be using collect, right? You should never use collect. All right. You talk, you say these things, but I was just talking to somebody about the Gaussian mixture in Spark. And essentially, they pull back a gig worth of data, do something locally, and then push a gig worth of data back out in broadcast variables. All right, any other questions? Yes.
How do you do this if you're a PySpark user, this debugging right now?
How do you do this if you're a PySpark user? Well, you learn Scala. That's the answer, right? So I get asked a lot of times, because I deal with a lot of people who do machine learning at Blizzard and other places, can I use PySpark? And so while I was at Cloudera, we did lots of tests to see, like, is it as performant? PySpark is about relatively as performant as the Scala is. The Java is just disgusting. Don't use the Java. It's just, if you like to type. If you like to type more, use the Java version. But apart from the debugging, this is the feature that I think, that I don't understand why people would use PySpark. This feature right there. I hit Control B, and I am in Spark code. And how many people have run into a bug with Spark? If you haven't raised your hand, then you haven't used Spark enough, right? Things blow up, and you're like, what happened, right? I mean, I remember back in the day when Spark SQL, whenever you used a group by, it would use the group by function instead of the reduce by function. I don't know if that's been fixed, but in the old days, if you had any type of skew, things would blow up. And you wouldn't know that unless you dig down into it. And the other thing is, and I know this may seem a little extreme, I can debug inside Spark, right? And this is how, I was talking about the Gaussian mixture and how I was pissed off about its implementation. This is how I figured out how it worked. I debugged through it and watched it. But I think if you're going to be in that world that you're going to do divide and conquer a lot, like the mortgage thing, I think Python makes a lot of sense, because then when you're in the divide and conquer land, you can use a lot of the machine learning libraries that Python has, and you can feel comfortable and happy and stuff like that. But if you're not that type of person and you're going to be a more generalized Spark expert, like if you want to put Spark and be a Spark expert on your resume, you really should probably have Scala Spark experience. At least that's my biased opinion. So all the Python people can yell at me afterwards. So any other questions? Nope. All right. Cool.
Let's
thank
thank
you.
Ted Malaska.
Give a big head to Ted. And if you do a Cartesian join between Nick, Ted, and me, what do you get? Coleman hairstyle.
Ah, there you go. No, but if I had any time, I can show the Cartesian stuff.
Are all the Databricks guys here?
Is he there? He's there.
We only
You're
got
good to go.
two. We only got two. Okay, well, we got to go. Anyway, we're going to try something different. You know, we've been hearing presentation for a while, and so what we're going to do now is we're going to have Michael and Hussein. I don't know if Tim is here, Eric is here, or TD is here. So what we want to do is we're going to change the format a little bit different because we've been doing it traditionally for about 10 summits. We do Ask Me Anything About Spark. No personal questions, ask me anything about Spark. And I'm going to introduce Michael. Michael has been working with Spark since the early days in AmpLab, before it was Apache Spark. So he's got his code prints and footprints all over the place. He's the guy who's responsible for Spark SQL, and more recently, he's been working on Spark streaming, and he's doing a keynote tomorrow as well. And so those of you who are attending the summit, make sure he's there. So big welcome to Michael. He's going to say a couple of things, and he's going to introduce Hussein himself. And they're going to tell what their subject matter expertise is. You can ask them any questions you want about Spark and Spark R and whatever. Here you go, Mike.
Oh, cool. Thank you very much. Jules kind of did the introduction, but yeah, I've been working with Spark for just about 3 years now. I'm the initial author of Catalyst and Spark SQL, and I'm doing a lot of stuff on structured streaming now. But please ask questions about anything. And I think, let's let Hussein in.
Hello, everyone. I really hope TD and Tim also show up. The main area that I feel I can have some answers would be probably Spark R among these other folks, and maybe a little bit of MLlib.
By the way, can we suit up? Maybe can we use mic 3 as well? Maybe we'll give them mic 3.
Yeah, I was wondering about PySpark efficiency versus Scala. I've heard contradictory kinds of stories. I mean, there's certainly overhead with PySpark, and I was just wondering if you could quantify that or talk about some of the issues.
Check this out.
Okay, good question.
Number 3.
Hello.
Oh, there we go. There we go.
Okay, so the question was, there's been a lot of talk of PySpark and overheads, and can we quantify or clarify the issues? So let me first make like an official Apache Spark statement. I want PySpark to be I'm like a huge Scala nerd, but I want PySpark to be as good as Scala Spark, and we've actually put a lot of effort into that, and I think it's rapidly approaching that. And in fact, one of the key things that has been a goal with structured streaming has been to, as we add APIs, in every case where it's possible, also make sure that we add those same APIs to PySpark. So how should I reason about performance here? I think there's a couple of different ways to look at that. One is, if you're working with pure SQL, if you're working with pure data frames, if you're writing code where basically it is Catalyst and Tungsten, the execution engine that's actually doing the processing, there should be no difference between PySpark and Scala Spark or Java Spark or even R Spark or just pure SQL. Basically what's happening is you're creating a logical plan using the language of your choice, and then it's getting tossed at the execution engine. And the construction of the logical plan is like 10 milliseconds, and then everything else is running exactly the same after that. Things change as soon as you start including your own code. So if you have a UDF in your SQL statement, we actually have to invoke Python in order to evaluate that UDF. And so what's actually happening under the covers is on each executor node, we are forking a Python process and piping data into it and then getting the answers out. And of course, there's some overhead to that. I think it's, it can be significant, but honestly, it's really hard to quantify because it has a lot to do with how fast is your Python code compared to your Scala code, and not even just the overhead. So really, I think the way I like to think of it, though, is more, how long is it going to take me to get my answer? If it's going to take you 6 months to learn Scala, and it's going to take your query an extra 20 minutes to run, does it really matter? But really, I think, from my standpoint, the thing I would love to hear is what are the missing features of PySpark that you hear Scala users talking about, so we can make sure we kind of keep these two languages equal as far as Spark goes. Does that answer your question?
Yeah, but I mean, don't you typically have a lambda that you ship across? So you're saying that
Yeah, it will always be there will always be overhead because we have to evaluate your Lambda. But if you're doing, actually, I would say in a majority of Spark SQL programs that I write, I use pure data frames. Like, but even machine learning, we're doing more and more with data frames. Like, there's quite a few expressions. And the nice thing is, when you use expressions inside of PySpark to construct, your machine learning functions, that's all being compiled down to super efficient bytecode.
So I would add one thing that is being planned and worked on is binary compatibility between JVM and Python and also R. There's an open source Jira about it. Once that's completed, they will be even more compatible in terms of performance because they can share data. Basically, we remove one serialization, deserialization step in execution of UDFs. So things are improving. What was the Jira again? I forget the Jira number. You should.
It is in Matei's keynote tomorrow. I promise the Jira number, but I don't remember what it is off the top of my head.
So another streaming question. I'm curious what you're doing with respect to like Beam feature capabilities or being basically an engine underneath Beam, Apache Beam.
Yeah. So you're talking about like the Beam API executing on top of Spark?
Yeah, or just having Spark streaming APIs that are comparable to Beam.
Yeah, so I don't know very much about the Beam execution engine for Spark. I've like consulted a little bit with the developer, but like I don't actually know the state of the project at this moment. I will say, as far as providing the same capabilities in structured streaming, I think we're actually pretty much approaching parity. We have event time, we have watermarks, we're adding map with state, we have UDFs, we have aggregations, we have data sets. So I think you should just use data frames and data sets, but I'm super biased. So please, if there are features in Beam that are missing from structured streaming, let me know. I would love to add them.
Yeah, actually the Beam folks like maintain a page with a compatibility matrix.
Is it up to
Spark
date?
does not look very good in that matrix.
Yeah, I bet they're comparing with D-streams and not structured streaming though. So I would agree. If you compare with D-streams, you're missing all those things I just listed: event time, watermarks. You do have map with state, but I think exactly one's processing when writing the files, like all of that is missing from D-streams. All of that does exist in structured streaming.
Fair enough. Thanks.
Hi, I have a couple of questions. First one, maybe simpler one, is the adaptive shuffling. When is that going to come for like production, kind of not alpha or beta, which is right now?
I don't know the answer to exactly when, because honestly, we're not spending any resources on that at the moment. But I can tell you the reason.
That's kind of an answer.
It's not turned on right now because there is one edge case where it makes joins slower, and it's really hard to fix that edge case. So I do know people who are running it in production today. It's not because the implementation is unstable. It's because, as with many optimizations, it's hard for them to be globally optimal, and it's not globally optimal, and that's why it's not turned on. So if it makes your workload faster, you should turn it on.
No, it doesn't.
No. Well, then maybe we should find another optimization.
It's not working, so there are some problems with skewed data. So
I see.
Eventually, hopefully one day that will get fixed. So the other question was that this data frame, data set talk is like are they going to be for some specific areas, or it's going to happen like what happened with MLlib for oddities, that eventually that it's going to be data sets and not data frame anymore? What is going to the future relationship between data sets and data frame? Because the API is completely different, and when approaching it from a development point of view, it's kind of a decision to make.
Yeah, so as of Spark 2.0, data frames and data sets are the same class in Spark SQL. They're just different ways to view your data. And I think the right way to think about it is when you're working with data frames, you're working with generic row objects. So the Scala compiler or the Java compiler does not know the types of your classes. It's kind of like working with SQL, where you just have these generic rows that are containers for your data. When you move into data set land, the only difference in execution is you add this thing called an encoder to the query plan, which says, hey, if I have a function that's actually going to get some data that comes out of this data frame, here's how I want you to represent it to my program as an object. And at the last minute, we take that encoder, we give it the binary data that comes out of Tungsten, and we construct an object and hand it to you. But other than that, all of the actual execution between data frames and data sets is the same. It's just different ways to view the data when your Lambda functions are involved.
Okay, so maybe I can rephrase the question. Is that going to be a flavor of the MLlib library for data sets, not for data frames?
Hi. They will be eventually. For now, we are mostly focusing on consolidating all the algorithms part of the Spark MLA package into the Spark ML package. And once we have done that, then we're going to explore how we can integrate data set as well.
Okay. Thank you. Thank you very much.
What would be a recommended way to go about getting something like a count distinct of devices over a cumulative time period?
Sorry, are we talking about like
Cumulative.
cumulative time period?
Sorry, are we talking about batch data or streaming data?
Just say Spark SQL.
Spark SQL.
So I guess I don't understand the question. Like, what's wrong with count distinct? Maybe would be a good.
Being able to see a count distinct over, so one day, and then a count distinct including the first and second day. So a window function, essentially.
I see.
I've had a hard time implementing that.
Yeah. So have you tried window functions?
Yes, it doesn't support count distinct.
Oh no! Well, we should add that. Open a Jira. Yeah, that's the right answer is window functions, and we should add count distinct.
And is there any planned support for correlated subqueries?
We do have some support for correlated subqueries. It's not complete.
But where the the correlation is between two objects instead of a straight equals, it's not supported right now.
Oh yeah, like where we need interval trees to to evaluate it. No, there's no plans. But open a Jira, open a PR, open source software. This is the first I've heard a request for that. But
okay.
Let us know what you're missing.
I have two questions. Question number one is about Java. I kind of feel that over the past maybe 2 years or so, it seems to maybe have been a bit deprioritized. So I'm wondering what your thoughts might be about that.
That has certainly not been our intention. I would say actually one of the huge pushes with Spark 2.0 was to make the Scala and the Java API the same so that it would not be deprioritized. So that you just have one API that all the features go into. I can tell you, me and Reynold argue every day about which features I'm allowed to use so that it all works in Java as well. That's not going to say we're certainly not perfect. So if there are cases where there are things you cannot do in Java, please let us know so we can fix them. But
so like my example is, for example, implementing custom pipelines in ML in Java.
Well, it's just like the rest of the Spark APIs. They are designed and they are meant to be used as well in Scala and Java. Do you have a specific example you're thinking of when you say that it's being deprioritized?
Well, I just mean that the API in Java, I believe, doesn't work. Well, it does work in Scala, and you have to work around it.
Okay, it's
needs more test cases. Please submit a bug.
Please, if you find some corner cases that for which you're having some trouble, it is a bug. It is not a feature. I tried. I really tried hard, and it is still a bug.
My second question is also about ML. So in MLlib, most of the machine learning algorithms have a simple method to, given a single example, get the prediction back. So it's great for using just behind a REST service or anything like that. And I noticed that in the data frames API, that is not there. So wondering about any thoughts about that.
You don't mean the transform API? Would that fit?
Once you have a model, yes, and you want to transform.
Once you have yes. So we had the conscious decision of separating the model from the actual pipeline, so that you could, so it offers several benefits. One of them is that you can, if eventually you can optimize the pipeline separately from dumping the models. And also, we have seen some use cases in which people wanted to have both, wanted to save both fitted and unfitted pipelines. So either models or the pipeline. And it really helped, especially with respect to compatibility with the other languages, to separate the two.
Okay, thank you.
Hello. Couple of questions about ML. One is regarding the neural networks, specifically being able to actually see some of the details once the model is built in terms of weights, things like that you typically do with more small-scale data sets. And also related to the model tuning. So it seems like model tuning is one of the hardest things once you get with working with ML. Any ideas on that or thoughts?
So if I understand correctly, the first part, is your question about introspecting what has been learned with multi-layer perceptron? Yeah.
Right, exactly. Going into the model and actually trying to analyze it a little bit better. Arguably, yes, a neural network is a black box, but still being able to actually delve into it.
Yeah, so right now we have, there are very limited APIs into accessing the content of the models. This is a bit on purpose so that then we have more flexibility into how we implement it. And the best way for that is either to do the developer APIs or or directly to access the contents of the private part of the model. That being said, if there are some, we always want to see some feedback about the APIs. And if you have a use case for that, then by all means, feel free to open a Jira and comment on it so that we have a better insight as to what is happening there. Regarding tuning, do you have some specific example in mind?
Well, basically, the idea being that, again, it kind of ties back to the opening the black box. Unless you actually see the model in details, you don't exactly know how to tune the model for better or, so all the things that you have is the validation sort of typical metrics, but you don't necessarily have a handle on which knobs to turn to improve sort of.
Yeah, so if you are working at the level of a pipeline, then you can always access the stagers, and then from the stagers, you can access to the different models and to the different estimators and regressors. But I'm under the impression that this would not be enough to satisfy your requirements, right? So do you mind if we take this question? I feel we could go really deep into this question, so I think it's better if we address it offline after this.
Okay, so we have 3 pending questions. 1, 2, 3, 4. Remember your number because I'm going to forget.
Okay, I have 2 questions. The first one, is GraphX dead?
No.
So is it going to be expanded upon or no?
More development is happening.
Yeah, so like the RDDs and data frames, we are trying to put as much effort as we can on graph frames. And the reason why we have not embedded it inside Spark so far is because it is missing some crucial graph-specific optimization, especially partitioning the data set, which are available in GraphX but not in graph frames. And this is going to be, I think, a topic for the next year. And because it ties deeply into into Catalyst, the SQL optimizer. So it is not dead. We actually still have some patches coming in for fixing some, mostly for fixing some bugs and some correctness issues.
Okay, cool. And my second question is, so in the original MLlib version of the machine learning library, we used to do a lot of changing the optimization algorithms to make it faster. So it seems like it's more difficult to change the optimization internals in the data frame space version?
Are you talking here from the perspective of a developer or from the perspective of the user who wants to change the optimizer, for example, of certain algorithm?
Like if you want to do your own version flavor of gradient descent.
Yes. So yeah, for doing that, there are some JIRAs that talk about adding this API. I mean, fairly the API for Spark.ml is fairly recent, and now we are looking at opening it up, especially for this kind of request coming in here. So by all means, please comment on the tickets, and so that we have a better perspective as to what would be useful for the users in this respect.
Hi, have you given any thought to putting on your roadmap exposing the scheduler backend so that people can more easily write third-party scheduler backends?
Yeah, I think there's a ticket open for that right now, in particular with respect to Kubernetes. So that's definitely being considered. I think the current thought is, like, I think what's happening right now is the Kubernetes effort is like trying it in a fork, and then once there's a proposed API, there'll be discussion around it, and hopefully we can actually merge that kind of new open API into Spark to allow other schedulers to plug in. But there's definitely discussion for it. If you're looking for the Jira, look for Kubernetes.
What is the plan for the next round of optimizations for Apache Spark SQL and Tungsten?
Yeah, anything more specific?
Well, I mean, right now, as Reynold explains it, it's writing freshman Java code to do that, right? It's not vectorized code that would implement the Spark SQL at a higher bandwidth more efficiently, right? I mean, there's at least a 5 to 8x additional performance possible. So I'm just wondering what's the next steps to get there?
Okay, I see. Honestly, that's actually not where we're focusing our effort right now. I think most of the effort that's going in here is in making it more pluggable. So Matei is going to talk tomorrow in his keynote about some ideas that we have to basically stabilize the binary columnar format that the internal execution engine uses to allow other data sources to plug in more efficiently, to allow Python UDFs to execute more efficiently, and things like that. So really, in terms of the bottleneck, it turns out we don't see the current lowest hanging fruit as that freshman who wrote a pretty tight for loop. We see it more in the getting data in and out of that execution engine. And I think that's where efforts in the next 6 months to a year will be focused.
Thank you.
Jules, how many more questions after this one?
We can take about 3 more questions.
3 more questions. Get down here.
Hi guys, thanks for taking the questions. Our use case is analyzing time series. Currently, we're not using Spark, we're using some other different technology. I'm wondering if Spark offers nice facilities for example, joining 2 time series, right? If you look at like just regular join in SQL, you have 2 keys where you join by equal. Time series, for example, you would want a point from one time series and join with a different point where an event occurred before that time, right? Or exactly at that time or before that time. And does Spark offer something like that?
Yeah, so we don't have point-in-time joins yet. There have actually been a couple of pull requests that basically added interval tree-based joins to Spark. Unfortunately, the author never took him across the finish line. But I think what that tells you is it's not super hard to add. So if there's enough demand, that's absolutely something we could put in there. I'll also say there is a Spark time series library that I'm not super familiar with, but it might be something to look at as well. I think it's made by Cloudera. But yeah, I think it's definitely something to consider, but it's not on my immediate roadmap.
Okay, thank you.
What's that? Sorry.
He left Cloudera, the person who wrote that. But time series in general is not difficult to do outside if you're not using SQL.
there's many methodologies. You can use the group by thing I talked about, or the windowing thing I talked about. I would have to know the exact use case for this, but there's lots of tricks you can do if it doesn't get solved by SQL. And there's a lot of things that don't get solved by SQL. SQL doesn't solve everything. And if you're trying to solve everything with SQL, you're eventually either going to have really crappy SQL or, yeah.
No, I mean, absolutely. This is why we added data sets and all these other APIs on top.
Structured streaming TD guy is over here, so you're going to ask him a question about structured streaming, please feel free.
I have a question on the core Spark. Is there any plan to make the external sorter pluggable? Because I did some work in Apache, MapReduce to make the sort pluggable. I can contribute, but is there any plan to do that?
You're the first time I've heard anyone ask for a pluggable external sort. We could do it, but there'd have to be enough demand. There'd have to be a proposed API. It would have to be good and not regress the existing ones. But then, yeah, absolutely, we consider it.
Okay, so can I raise a Jira ticket on that?
Anybody can open a Jira ticket. So yes, please do.
Okay, thank you.
Any questions? Nick.
So this is kind of on behalf of some of my coworkers who work with R. And I found out that a lot of them are using something called Sparkly R to use R with Spark. I don't know anything about R or about that, but I'm on the data engineering team, so I was curious, like, why aren't you using Spark R? And they had a bunch of complaints. I was just wondering, what's the comparison in your mind between Spark R and Sparkly R, and where do their trajectories go?
Okay, so there's going to be a talk about Sparkly R by someone from R Studio, I believe tomorrow, or maybe on Thursday, but definitely go to that, or encourage your colleagues to go to that. There's, I think, at least 2 talks about Spark R. So those are also, there's talks about Spark R as well. Very high level, very, very high level. Sparkly R claim, this is their mission. They have built an opinionated API, R API on top of Spark data frames. So what they mean by opinionated is that they basically take dplyr and built a Spark backend for that interface. And dplyr, a lot of data scientists and a lot of our users have converted to the dplyr style of API over the traditional R data frame API. So that's the Sparkly R mission. On the other hand, Spark R, the general vision was be very much compatible with existing R data.frame API. In that regard, it is not an opinionated API. So that's one thing. And on the other hand, Spark R also kind of ties a little bit deeper with Spark. So for example, it has added UDF support. I'm going to talk about that on Thursday, how to parallelize existing R packages. So in that regard, is slightly different. So basically, these are 2 different R packages that enable you to talk to Spark from your R code. One, it follows one style, the other one doesn't follow that style, and they don't have exactly 100% overlap in terms of features. So it's, I think, a good thing. There are now 2 things you can choose from. Hopefully, the 2 projects learn from each other and improve each other.
Thank you.
Hi. So, is there any support for geospatial analytic queries in Spark, especially from the streaming part from IoT devices?
So yeah, okay. So there definitely wasn't a package built on top of Spark SQL for doing geospatial stuff. We were just trying to remember the name of it, but I do know the name of the guy who made it, Magellan. That's it. I knew it was a cute name. Yeah, Magellan. So I would recommend checking that out. It was a library that basically added a whole bunch of UDFs. I think the nice thing about that is since it was built on top of Spark SQL, it would work with Spark streaming.
Okay, great.
Or structured streaming.
Okay, and then this last question. How is Spark moving into the sort of GPU computational or computations on GPUs or NUMAs?
So definitely the GPU computation is a very interesting topic, especially when you do a neural network and deep learning computations. In that respect, so far, because it adds and pulls so much dependencies, we try to keep interfaces at the level of the Spark package or at the level of the developer APIs, so that then the problem from the perspective of Spark is how to transfer efficiently data from the tungsten representation into the memory managed by the GPU. And so that limits the interface. And so that means we don't need to maintain a whole separate package related to accelerated hardware. That being said, most of the libraries that are being supported or explored right now are mostly numerical libraries. And I think that ties a bit into a previous question about whether there was support for accelerating other part of Spark, such as the SQL engine. And I believe that so far, this is there hasn't been such a push like it has happened for deep learning.
All right, guys, on closing remarks, give a big hand to TD, Michael, Hussein, and Tim for taking your very pointed Spark arrows and then deflecting it back to you. So give a big hand. And also Ted for giving us an insightful thing how to debug. And learn Scala, as you say. And thank you for Jag, who's gone, disappeared. But thanks for hosting, and thanks for sponsoring us. And see you guys tomorrow morning, bright and early, at Keynote. Thank you.